We just had a magnitude 4.7 earthquake hit Campi Flegrei directly, and this is a genuinely big deal. Campi Flegrei is Italy's supervolcano, sitting just west of Naples, and it just produced the strongest earthquake it has recorded in the modern instrumental era. Let me say that again so it lands. DS. This is the strongest quake this system has thrown since we started tracking it closely. Not the strongest in a decade, the strongest, period, in the current record. If you follow this region even casually, you know that sentence alone should stop you in your tracks. Because Campi Flegrei doesn't produce headline events often, and when it does, they tend to mark a real shift in behavior rather than background noise. Here's why that matters. Since around 2005, Campi Flegrei has been on a slow, grinding upward trend in seismicity, gas emissions, and ground uplift, a phenomenon called bradycism, where the ground literally rises and falls as the system beneath it breathes. That upward trend went exponential starting in 2020. We had Signify, caught seismic swarms in 2024 and 2025, including bursts of nearly 1,000 small earthquakes in a matter of weeks. But here's the thing about how earthquake energy scales. A swarm of 1,000 small quakes can release less total energy than a single, much larger one. Energy doesn't scale linearly with magnitude, it scales exponentially. Each whole number step up in May. Ionitude corresponds to roughly 32 times more energy release, which is why a magnitude 4.7 releases roughly 3 times the energy of a 4.4, and dramatically more than any swarm of small tremors combined. So when I tell you this, 4.7 is the strongest event of the entire monitoring period. I mean that it plausibly outweighs, in raw energy terms, every other recorded event stacked together, including all those dramatic-looking swarms with hundreds of individual quakes on the map. For scale, INGV, Italy's geophysical monitoring agency, classified this event as 4.7 with an uncertainty band of plus or minus 0.3, meaning it could technically be as high as magnitude 5. USGS, which relies on a lower density global network, logged it as 4.5 and placed the epicenter somewhat off from Solfatara, the crater hour, IA known for its sulfur vents and fumaroles. INGV's local network is denser and built specifically for this region, with instruments placed much closer to the actual source, so their number and their location are the more reliable ones here. And their number puts the epicenter almost direct, lie beneath Solfatara at a shallow depth of around 2.5 kilometers. That shallow depth is exactly why this quake did real damage, even though 4.7 sounds modest on paper. Shallow earthquakes hit the surface harder because the seismic energy has far less rock to travel through and dissipate across before it reaches you. Hess buildings and roads. Buildings collapsed, roads cracked open, there were landslides, boulders coming down slopes, cars crushed under debris. None of that is typical for a 4.7, unless you get depth this shallow combined with older, more vulnerable construction, which is exactly the situation in this part of Italy, where many buildings predate modern seismic codes by decades or even centuries. Since that quake, more than 90 aftershocks have been recorded, including a 3.8 at a similar depth, suggesting fresh movement or a new pulse of fluid or gas pushing into the same fracture network. All of this activity is clustering directly beneath Solfatara, right at the H-jaws, of the system, not off to the side, which is what makes this sequence particularly worth watching. When aftershocks stay concentrated at the core of a volcanic system rather than migrating outward, it usually points to a localized process still actively working through that same patch of crust, rather than a broader regional adjustment settling down. Let's talk about what Campi Flegrei actually is, because the shape of it explains a lot. It isn't one crater, it's a nested structure, an outer caldera rim, an inner caldera inside that, and smaller collapse structures nested within the inner one, the product of at least 2 enormous prehistoric eruptions layered on top of each other over tens of thousands of years. The Bay of Pozzuoli exists because this whole system has collapsed catastrophically in the past, with the roof of an emptied magma chamber subsiding to form the basin that's now partially filled with sea, water. Underneath it all sits a magma system that inflates and deflates over time, sometimes over years, sometimes over just months, as pressure and fluid volumes shift below. When it inflates significantly and then ruptures, you get a caldera-forming eruption, and the ground above the drained magma chamber subsides, heat times dramatically, reshaping the coastline in the process. This is a system that Italian volcanologists themselves classify as a supervolcano, based on its eruptive history and the sheer volume of material it's capable of producing, potentially in the range of tens to over 100 cubic kilometers of dry rock equivalent material for its largest known eruptions. It hasn't produced a major eruption since Monte Nuovo, roughly 5 centuries ago, a comparatively small event by the system's own historical standards, but its deeper record includes genuinely enormous events, including the Campania N Ignimbrite eruption tens of thousands of years ago. one of the largest volcanic events in Europe's history, one that likely affected climate and ecosystems across a wide swath of the continent. Right now, geologists are focused less on that ancient deep magma system and more on what's happening structurally in the top few kilometers of crust. There's a well-documented caprock layer beneath the caldera, identified through seismic imaging and resistivity surveys. And this caprock is essentially what's holding G-pressure back from a very active hydrothermal system underneath. Superheated fluids and gases are moving through this shallow zone, creating microfractures. And that fracturing has been intensifying for years as repeated bursts of seismic energy work through the same rock over and over. Think of I. T in terms of a cycle. A major eruption is a rupture event, followed by a healing phase where new caprock gradually forms as minerals precipitate and seal fractures back up, followed by a loading phase where pressure builds again beneath that renewed seal, followed eventually by another rupture once the accumulated stress exceeds what the rock can hold. Right now, everything about the data suggests we're deep in a loading phase, and this magnitude 4.7 represents the caprock taking another serious hit, one more crack in a structure that has already absorbed years of repeated stress. It's also worth being clear about what's driving this activity. Volcanic systems aren't simple tanks of liquid rock sitting under pressure waiting to blow. Beneath Campiflegrei, there's a complex mixture of partially molten material, some of it liquid magma, much of it a crystal-rich much that can behave more like a slurry than a fluid, full of suspended crystals in varying proportions. Under the right conditions, changes in temperature, pressure, or the introduction of fresh, volatile-rich magma from depth, that mush can remobilize, becoming more fluid and more mobile, which is one of the mechanisms that can precede larger unrest, or even eruption. Whether that's happening at depth right now isn't something anyone can say with certainty given the tools we currently have, but the surface signals, rising gas flux, sustained ground uplift, and now this record earthquake are consistent with a system where pressure is building somewhere in that shallow to intermediate crust, even if we can't pin down the exact depth or volume involved. Zooming out to the broader region helps put this in context too. Just months before this quake, there was a deep magnitude 6 earthquake roughly 375 kilometers down, in a location close to Campiflegrei geographically, even if far below it in depth terms. Almost nobody, at the surface, felt it because of the depth. But deep focus earthquakes like this are unusual and not fully understood. They aren't happening on ordinary faults the way shallow crustal earthquakes do. And some researchers link them to mineralogical phase transitions deep in subducting material, essentially rock changing its internal crystal structure under extreme pressure in a way that can suddenly... There's one more thing missing this year that would normally help. India has a second climate pattern out in the Indian Ocean that can sometimes push back against El Niño and drag moisture in any way, and it has rescued the monsoon before. This year, it is sitting neutral, doing nothing. There is no counterweight this time, which is part of why the swings this year have been sharper than they might otherwise have been. Europe has just been through something without precedent, and it's worth addressing directly because the timing makes it easy to draw the wrong conclusion. Western Europe recorded its hottest June ever measured. France had its hottest day in its entire history. Germany broke its national record, and Barcelona hit 40.5 degrees Celsius. That's on the 8th of July. The estimated death toll runs into the thousands, and the story wrote itself because a record Pacific and a record Europe in the same summer are obviously connected. Except they aren't. When researchers ran simulations on this heat wave, the answer came clean. El Niño played no role. Europe's heat was a heat dome, parked over the fastest warming continent on the planet, now about 2 degrees hotter than it was in 1976. So why does this matter for our story? Because it tells you when El Niño's bill actually comes due. This event was declared only a few weeks ago, and its grip on the northern half of the world doesn't show up in summer. It shows up in autumn, in winter, and in the year that follows. Europe's June heat wave wasn't El Niño. It was the floor that El Niño is about to be stacked on top of, and Europe's own El Niño-driven winter hasn't happened yet. Here's something that surprises most people when they first hear it. A super El Niño actually makes the Atlantic hurricane season quieter. Not safer everywhere, but quieter in the Atlantic specifically. When the Pacific Ocean heats up dramatically, it changes the wind patterns high up in the atmosphere over the Atlantic and Caribbean. Those winds create what meteorology STS call wind shear, powerful gusts at high altitude that tear developing hurricanes apart before they can grow into anything serious. Hurricanes need calm, consistent conditions to strengthen, and wind shear is their enemy. A strong El Niño fills the Atlantic with it. This is why NOAA's outlook called for a below normal Atlantic season, and why Colorado State University cut its forecast in June to around 11 named storms, roughly 60% of a normal year. But here's the catch. The Pacific gets the opposite. El Niño warms the eastern Pacific, reduces wind shear there, and creates ideal conditions for storms to develop and strengthen off the coast of Mexico and Central America. So while on The ocean calms down, the other heats up. The Atlantic quietens. The Pacific intensifies. And whether that trade-off works in your favor depends entirely on which coastline you call home, and for anyone on Mexico's Pacific coast specifically, the coming weeks are exactly when that heightened storm activity would be expected to show up. This is the part that actually matters for most people watching this, because a super El Nino doesn't feel the same everywhere. Depending on where you live, it either brings too much water or not nearly enough, and understanding which side of that line you're on is the key to knowing what to actually expect where you are. Start with North America, where the effects depend heavily on where you are and where most of the strongest signal still lands in winter rather than right now. The southern United States, from California across Texas to Florida, typically turns wetter and cooler as a more active jet stream drags storm after storm across the region. Hitch for a drought-stricken southwest is mostly welcome, and for low-lying areas means flooding. The northern tier does the opposite. The Pacific Northwest and the northern Rockies run warmer and drier, with reduced mountain snowpack. And that thin snow matters more than it sounds because it's a water supply released slowly through the summer. So losing it dries everything downstream out faster and stretches the wildfire season. The upper Midwest generally gets a milder winter, several degrees above normal. Up in Canada, the same split holds. The western provinces tend to run warm and dry, which raises drought and fire risk across the prairies in British Columbia, while the effect fades the further east you go. The East African regions, including Kenya, Somalia, and Ethiopia, typically see above-average rainfall during El Nino, which sounds like good news until you see what that actually looks like on the ground. The 2023 to 2024 El Nino, which wasn't even a super event, caused devastating floods across the region that displaced hundreds of thousands of people, and this year's event is already tracking stronger than that one was at the same point in its development. South America has already been introduced through Peru, but the damage doesn't stop at the coast. The Amazon basin faces drought and heat, which is dangerous in a rainforest already under enormous resource, since a large share of it is degraded, and a strong El Nino on top of that raises wildfire risk toward the levels of the catastrophic 2023 fire season. Further south, Argentina, Uruguay, and southern Brazil tend to get the reverse, with above-average rainfall and a raised risk of flooding in low-lying areas. Australia is the clearest signal of them all. El Nino and Australian weather are tightly linked because the warm water sliding east across the Pacific is warm water sliding away from Australia, taking its rainfall with it. That means a hotter, drier spring and summer across the east of the country, shrinking water supplies, stressed farmland, and a longer, more dangerous bushfire season, with the sharpest effects typically arriving as the southern hemisphere moves into its own summer over the next several months. Beyond the floods and droughts and hurricanes, there's a bigger thing that makes this different from every event that came before it. All 5 of those previous giants arrived on a cooler planet, and this one is arriving on a world that has just posted its 11 warmest years in a row. El Nino doesn't create heat, For years, the Pacific quietly stores heat below its surface, and El Nino releases heat that the ocean has been storing for years back into the atmosphere. That process consistently pushes global temperatures upward. The only difference this time is the starting point, the baseline. The planet is already warmer than it's ever been in the modern record. So when El Nino adds its heat on top of that, the numbers go somewhere new, and that's really the central reason this particular event is worth tracking closely rather than filing away as just another cyclical curiosity. It's worth understanding exactly how forecasters actually measure something like this, because the number quoted most often, the 1.2 degree anomaly, comes from a specific, carefully defined patch of ocean called the Nino 3.4 region, a rectangle of open water straddling the equator in the central Pacific. Agencies track the average sea surface temperature here and compare it to a rolling multi-decade baseline, and when that anomaly stays above roughly 0.5 degrees for several consecutive overlapping 3-month periods, it gets classified as El Nino. Above 1.5 degrees sustained, it starts getting called strong. This year's event crossed that T. It helps to put this year alongside the handful of previous events strong enough to earn the same label. The 1982 to 1983 event caught much of the world by surprise, partly because satellite. Still, this is the kind of event that deserves attention rather than dismissal. A supervolcano sitting beneath a densely populated bay, showing its strongest recorded seismic signal in the modern era, layered on top of years of rising gas output and ground deformation, is a story worth following closely, not because panic is warranted, but because complacency isn't either. Europe has a real interest in how this system behaves over the coming months, both because of the direct risk to the people living around Naples, and because a major eruption from a system this size would have consequences well beyond Italy's borders, potentially affecting air travel, agriculture, and climate across the continent depending on scale. the way past major eruptions from comparable systems have done elsewhere in the world. It's worth drawing a distinction here that often gets lost in coverage of events like this: the difference between a hydrothermal explosion and a magmatic eruption. A hydrothermal explosion happens when superheated water and steam trapped beneath a sealing layer of rock suddenly find a path to the surface, blasting through with enough force to throw rock and debris, but without fresh magma actually reaching daylight. These events can be sudden, dangerous, and destructive on a local scale, but they're a fundamentally different animal from a magmatic eruption, where molten rock itself is erupted, sometimes explosively, sometimes as flowing lava. Given the shallow depth of this earthquake and the intensity of the hydrothermal system beneath Solfatara, a hydrothermal explosion is arguably the more immediate hazard to watch for in the coming weeks, more so than a full magmatic eruption, which would typically be preceded by its own distinct set of signals, including much larger and more sustained ground deformation, a shift in the type of seismic signals recorded toward what's known as long-period or tremor-like events associated with fluid movement, and a marked change in gas composition reflecting fresh magma degassing rather than simply reheated groundwater and older volatiles working their way up through existing fractures. It's also worth putting Campi Flegrei in a wider global context, because people often reach for Yellowstone as the reference point for what a supervolcano means, and that comparison is useful but imperfect. Yellowstone's caldera system is enormous and sits over what's generally interpreted as a mantle hotspot, a very different tectonic setting from Campi Flegrei, which is tied instead to subductio, and beneath the Italian peninsula. Toba, in Indonesia, produced one of the largest eruptions in the last 100,000 years, and is often invoked as a worst-case reference point for supervolcanic eruptions generally. Campi Flegrei's largest known eruptions are on a similar order of magnitude to some of history's most significant volcanic events, which is exactly why Italian scientists use the supervolcano label at all, but it's important to say clearly that the vast majority of unrest episodes at systems like this one, including this current one, do not end in eruptions of that scale. Most unrest episodes at calderas worldwide resolve without eruption entirely, some over months, some over years, some, like Campi Flegrei's own multi-decade history, stretching out over generations. That statistical reality doesn't mean this episode isn't significant. It clearly is, but it's the context that should sit alongside any discussion of worst-case scenarios. On the monitoring side, it's worth appreciating just how much instrumentation is trained on this specific patch of ground. INGV operates a dense local seismic network purpose-built for Campi Flegrei, supplemented by GPS stations, tracking ground movement to within millimeters, tilt meters measuring subtle changes in slope at the surface, gas sampling stations at Solfatara and other Fumaro, fields tracking the chemistry of what's coming up, and satellite radar interferometry that can measure uplift and subsidence across the entire caldera from space. This is, without exaggeration, one of the most heavily monitored volcanic systems on the planet, precisely because of how many people live directly on top of it, and how much is potentially at stake if unrest continues to escalate. That level of monitoring is actually good news in one specie. Fixense. If this system does move toward a more serious phase of unrest, the odds of getting meaningful advance warning through some combination of these instruments are considerably better than they would be for a similarly hazardous but less monitored volcano elsewhere in the world. I also want to address something that comes up constantly in the comments whenever a story like this goes out: the temptation to connect every earthquake, every volcanic eruption, and every unusual weather event into a single grand unified narrative. It's tempting because the human brain is wired to find patterns and beak us. Use a tidy narrative feels more satisfying than the messier reality, which is that the Earth runs many mostly independent systems that occasionally cluster in timing purely by chance. Etna erupting around the same time as this earthquake at Campi Flegrei doesn't require a shared trigger. Both systems sit along the same general tectonic boundary, and both experience regular activity on their own separate cycles, so OV. Lapping episodes will happen periodically without needing an external cause. The responsible approach is to track each system on its own merits, using the specific data relevant to that system, rather than reaching for a single explanation that ties everything together. That's not a dismissal of genuine large-scale connections where they do exist and are well supported by evidence. It's simply a reminder that correlation in timing isn't the same thing as demonstrated causation. And good science requires holding that distinction carefully, even when a more dramatic story would be easier to tell. It's a discipline worth applying consistently, not just when it's convenient, because the moment you start accepting loose correlations as proof in one direction, you lose the standing to reject them in another. And the whole point of tracking this data seriously is to keep the analysis honest, regardless of which conclusion would make for a better headline. So where does that leave us? We have a record-breaking earthquake for this specific system, a shallow depth that amplified its destructive impact, a caprock structure that's been absorbing years of repeated stress and just took another significant hit. An active aftershock sequence, style L, working through the same shallow structure, and a broader regional picture showing elevated activity at other Italian volcanic systems around the same window of time. None of that adds up to a confident prediction of what happens. Hence, next, and anyone claiming otherwise is overselling their certainty. What it does add up to is a system that deserves sustained, careful attention over the coming weeks and months, tracked through the same instruments and the same data streams that have caught every meaningful shift in this volcano's behavior for decades. I'll keep tracking this closely and bring you updates as new data comes in from INGV, as aftershock patterns evolve, and as we get more clarity on gas emissions and ground deformation in the weeks ahead. This is a story that's still developing, and it's one worth watching with clear eyes rather than either dismissing it or blowing it out of proportion, because both of those reactions ultimately fail the people who need accurate information the most. If you found this useful, consider subscribing so you don't miss the next update, because a system like this one doesn't stay quiet for long, and when the next signal comes in, it's another quake, a shift in gas readings, or new deformation data from INGV, I want you hearing it from a source that treats the science with the seriousness it deserves, rather than chasing the most alarming possible headline. Thanks for watching, and I'll see you in the next one.